Okay, so let me also share my screen and bring up the PowerPoint here. Back here, let's see. Okay, so now we're in business. So as I was saying earlier, we'll be looking now at how ionization energy changes as you go across a period and down a group. But first, we have to define what we mean by this term ionization energy. So the definition is right here. It is the energy required to remove an electron from a ground state gaseous atom. All right. So whenever an atom in a gaseous state loses an electron, the only way it does that is if energy is used to remove the electron. All right. And that energy is known as the ionization energy. All right. And usually it's expressed in kilojoules per mole of atom. And of course, if you have a multi-electron atom, then of course you can have electrons being removed one at a time. So if you have, let's say, an M atom in a gaseous state and it loses one electron, then the ionization energy for that removal, we call that the first ionization energy. And then if you want to remove the next electron, that's called the second ionization energy, and so on and so forth. All right. So that's basically what ionization energy is all about. And as stated here, you can have more than one ionization energies, depending on the number of electrons that is present originally in the neutral atom. Now, what you're going to find when you compare all these ionization energies for the first, second, and so on, ionization, what you find is that the energy required to remove successive electrons increases, right? So a certain amount of energy is required to remove the first one, then to remove the second one, more energy is required, and then to remove the third one, even more energy is required, and so on and so forth, right? And the main reason for that is that if you think about it, it makes sense. If you're removing the first electron, you're removing that electron from a neutral atom, right? So that requires a certain amount of energy. But to remove the second electron, now you're going to remove an electron, which by the way is negatively charged, from something which is already positively charged. So therefore, as you can imagine, trying to remove electrons from something which is already positively charged will require more energy than removing from the neutral atom. And then as the charge increases with each successive removal of electrons, it becomes progressively more difficult to remove each electron at each step. All right, so that's what you find. You'll find that the lowest energy or the lowest value of the ionization energy for any atom would be the first, would be the one corresponding to the removal of the first electron. And then it becomes progressively more difficult to remove successive electrons. All right. Now, what you'll find also is that there will be a large increase in the ionization energy when you compare removing the valence electrons to the inner core electrons. All right. Why is that so? Well, again, if you think about the atomic structure or how the electrons are distributed, that makes sense. Basically, what happens is that the valence electrons, of course, are the electrons which are in the valence shell, which is furthest away from the nucleus, right? So if you remove those electrons and then you start removing the inner core electrons, those electrons will be closer to the nucleus, and therefore there will be a more stronger attractive force between the inner core electrons and the nucleus, and therefore those electrons will be more difficult to remove compared to the valence electron, right? So the valence electrons are easier to remove because they are on the outermost shell, they're furthest away from the nucleus, and then the inner core electrons will be more difficult to move because those are closer to the nucleus, right? Now, in terms of trends that you would observe across a period and down the group, let's look at what happens as you go from top to bottom of any group. What you're going to find is that as you go down the group, the first ionization energy, so to remove the first electron, right? The first ionization energy will decrease, right, as you go down the group, all right? So if you take, for example, group 1A, which starts with hydrogen at the top, right? And then you go to lithium, to sodium, and so on, it becomes easier to remove the first, the valence electron, the one electron on the outermost shell in each case, all right? Why does that happen? Well, again, if you think about how the electrons are arranged, it makes sense because as you go down the group, what happens, there are two things that happen. One, the distance between the valence electron and the nucleus increases, right? And not only that, as you go down the group, there are more inner core electrons between the nucleus and the valence electrons, right? So there's a shielding effect that the inner core electrons will have on the valence electrons. So those are the two factors which basically causes the first ionization energy to increase as you go down the group. The first one is the distance that occurs. Hold on, what's going on here? The distance between the nucleus and the valence electron increases as you go down the group, and also there's increased shielding due to the inner core electrons between the nucleus and the valence electron. So therefore, those two factors basically reinforces the release of an electron or makes the valence electron easier to remove, and therefore, as a result, the ionization energy increases. So that's what happens as you go down the group, all right? Or go down any group for that matter, all right? Now, what about going from left to right of any period? Okay, so what you'll find, if you look at the data, what you're going to find is that generally, there are a couple of exceptions, which we're going to get into, but generally speaking, as you go from left to right of any period, the ionization energy, the first ionization energy increases, all right? So if you take, for example, period 2, starts with lithium and ends with neon, what you're going to find is that as you go from lithium to beryllium, the ionization energy increases. In fact, I think I have some numbers here. Okay, so this small table here is showing you the first and second ionization energies for groups 1A and 2A, all right? So as I was saying, going from lithium to beryllium, you see that there's an increase in the first ionization energy, and you see the same thing for sodium going to magnesium, potassium going to calcium, and so on and so forth, right? And the reason for that is that if you think about what's happening, again, in relation to the electron structure, what is happening when you're going from one atom to the other in one period? You're making two changes. You're adding an electron to the same shell, and at the same time, you're adding a proton to the nucleus, right? The consequence of that is that the nucleus will become more positive and therefore have a greater attraction for the surrounding electrons, and therefore, as a result, it becomes progressively more difficult to remove that valence electrons, and therefore, the first ionization energy increases as you go from left to right of any period. Now, as I said before, there are some exceptions which we're going to get into, right? There's some other things I want to point out in this table here. Something I made mention of already. In the case of group 1A, right, for example, as you go down the group, the first ionization energy decreases. You can see that for lithium, where the first ionization energy is 520 kilojoules per mole, and then sodium 496, and then potassium 419, and then rubidium 403, and then cesium 376. So you see a decrease in the first ionization energy when it comes to the group 1A metals, and the same is true for the group 2A elements. Same trend, you see a decrease in the first ionization energy, all right? Okay, let me see here. There's something else I want to point out here. And that is that if you compare removing the first two electrons, let's say, okay, let's look at lithium, right? In order for you to remove the first electron, the amount of energy needed is 520. And then to remove the next electron, look at the amount of energy needed. That's 7,298, right? That's a huge difference between the energy required to remove the first and the second electron. Now compare that to beryllium, right? To remove the first electron in the case of beryllium, it's 900, right? And then to remove the second electron, it is 1,757. So you notice that this difference, you'll notice that this difference here, what's going on? You'll notice that this difference here is small compared to this difference, right? Now the question is, why is it smaller? Why is it that the difference between the first and second ionization energy in the case of beryllium is smaller compared to the first and second ionization energy in the case of lithium? Again, we have to go to the electronic arrangement, the electron configuration. In the case of beryllium, the electronic configuration is 1s2, 2s2, right? In the case of lithium, it is 1s2, 2s1, right? So in the case of beryllium, the two electrons that to be removed would come from the second shell, right? So therefore, the difference in energy required to remove both of them would not be that large, right? Because both electrons belong to the same shell, so they have about the same energy level. In the case, however, of lithium, the first electron will be removed from the second shell, and then the next electron will be removed from the first shell, which is closer to the nucleus, right? So therefore, there's a big disparity between the amount of energy needed to remove the first electron, which is removed from the second shell, and the amount of energy needed to remove the second electron, which will be removed from the first shell, which is significantly closer to the nucleus. So that's why there's a big difference in terms of the first and second ionization energies in the case of lithium compared to that difference in the case of beryllium. And you can use the same argument to explain this, a similar comparison between sodium and magnesium, potassium and calcium, and so on, right? Okay, I think that's all I can say about this diagram here, so let me move on. Oh, so here is where we're going to see the trend, as I said before, going from left to right, of any period in terms of the ionization energy. And remember I said, going from left to right, there's a general increase in the first ionization energy with certain exceptions, all right? Now, where are those exceptions? Let's look at period 2, starting with lithium, right? So in the case of lithium, the first ionization energy is 520, and then the second ionization energy is 900. Of course, no surprise there. As you go from left to right, the ionization energy would increase. But when you get from beryllium to boron, what do we notice? We notice that there's a slight decrease in the first ionization energy, right? Whereas in the case of beryllium, the first ionization energy is 900. In the case of boron, it is 801, right? So there's a slight decrease going from beryllium to boron. Now, why does that happen, right? Why is it that boron has a slightly lower first ionization energy compared to beryllium? Again, we have to go to the electronic configuration to explain that. Now, in the case of beryllium, its electronic configuration is 1s2, 2s2. That's beryllium, right? In the case of boron, its electronic configuration is 1s2, 2s2, 2p1, right? So, in the case of beryllium, to lose an electron, that electron would have been lost from the 2s sublevel there, right? But in the case of boron, the one electron to be lost would have to be lost from the 2p sublevel, which is of a higher energy, right? So therefore, because the 2p electron here is of a higher energy compared to the electron in the 2s sublevel, this electron is more easier to lose, and therefore less energy will be required to remove that electron. So therefore, for that reason, the first ionization energy of boron is slightly lower compared to the first ionization energy of beryllium, all right? So that explains the slight decrease as you go from beryllium to boron. And then if you continue to look at the other elements going from one atom to the next, you'll see that going from boron to carbon, there's an increase in the first ionization energy, no surprise there. And then when you go from carbon to nitrogen, there's also an increase in the first ionization energy, no surprise there. But then when we get from nitrogen to oxygen, what do we notice? There's a slight decrease in the first ionization energy, all right? So how do we explain that? Again, we'd have to go to the electronic configurations of comparing the electronic configurations of nitrogen and oxygen. So in the case of nitrogen, which has an atomic number of 7, right? So in the case of nitrogen, the electronic configuration would be 1s2, 2s2, and what I'm going to do here is use boxes to represent the 2p sublevel, right? So basically, you're going to have 1, 2, 3 electrons in the 2p sublevel, and of course, based on the Aufbau principle, we know that the electrons will be occupying the p orbital singly, right? So this would be the electron configuration of nitrogen. In the case of oxygen, the electron configuration is 1s2, 2s2, and then using boxes again to represent the two-piece sublevel. The distribution of electrons within the two-piece sublevel will be 1, 2, 3, and then 4, right? Now, basically, we have to compare these two in order to explain this trend where the first ionization energy of oxygen is slightly lower than that of nitrogen. And it has to do with the fact that in the case of nitrogen, when this needs to lose an electron, it will lose an electron from any one of these 2p sublevels. This is 2p, this is 2p, right? So it will lose one of these 3 electrons, and that would require a certain amount of energy. However, in the case of oxygen, because we have 2 electrons paired up within this particular 2p orbital, that means that one of these 2 electrons is more likely to be released because you have some repulsive forces that takes place between the 2 electrons that are sharing the same p orbital, right? So because of the repulsive forces that exist between these 2 electrons right here, one of these electrons will be more easily lost, and therefore the energy required for that would be less compared to the energy required for the removal of an electron from the 2p sublevel in the case of nitrogen. So that's the reason why the electronic configuration, I'm sorry, not the electronic configuration, the first ionization energy of nitrogen decreases slightly as you go from nitrogen to oxygen. And then when you continue to look at the other values, you see that it continues to increase as you go from oxygen to fluorine, and then from fluorine to neon, there's a general increase going from oxygen all the way to neon, all right? So that explains what I just described, explains the dip, slight dip in the first ionization energy, going from beryllium to boron, and then going from nitrogen to oxygen. And you see a similar trend in the first ionization energy for the elements that are just below the elements I referred to in the same group. So for example, in the case of magnesium, right, there's a corresponding decrease in the first ionization energy going from magnesium to aluminum, similar to what we saw going from beryllium to boron. And then there's a slight decrease going from phosphorus to sulfur, again, similar to what we saw going from nitrogen to oxygen above, all right? So the same idea that explains what I described earlier in period 2 is also applicable when it comes to going from magnesium to aluminum and going from phosphorus to sulfur, all right? So those are the exceptions, but again, remember, the general trend is an increase in the first ionization energy as you go from one element to the next across a period, with certain exceptions, such as the ones I mentioned just now. Okay, so let me, this is just basically stating what I said earlier. So let me move on. Okay, so this is a graphical representation of the first ionization energy plotted on the y-axis and the atomic number plotted on the x-axis. And you're going to see for period 2, starting with lithium and ending with neon, what I described earlier, right? So as I said before, going from lithium until you get to beryllium, you see that there's an increase in the first ionization energy, and then there's a slight decrease from beryllium to boron, and then as you go from boron to nitrogen, there's an increase or gradual increase, and then from nitrogen to oxygen, there's a small dip in the first ionization energy, and then from oxygen to neon, there's an increase in the first ionization energy. So that's basically what's being shown for this part of the graph, going from lithium to neon. And there's a similar pattern going from sodium to argon. There's a dip when you get down to aluminum, from magnesium, and then there's another dip when you go from phosphorus to sulfur. All right, and then what happens after that? It's more confusing. We won't get into a discussion of this part here. Things are a bit haywire, not as organized or straightforward when it comes to examining the trends in the first ionization energy. But still, I should say and reiterate that the general trend is an increase in the first ionization energy as you go from one element to the next. All right. Okay. So based on what we have covered so far, we should be able to answer these questions. So this question says, without reference to figure 8.15, which is the values of the energies given, first ionization energies given, it says arrange each set of elements in the expected order of increasing first ionization energy. So increasing means you're going to start with the lowest to the highest, right? Based on the relative positions of the elements in the periodic table, all right? So the first series given in A, whoops, is magnesium, sulfur, and silicon. So if you look at the periodic table, based on what I see here, they're all in the same period, right? You have magnesium to the extreme left, and then you have silicon somewhere in between, and then you have sulfur closer to the end of that period. Okay, so remember what we said. Going from left to right, there's a general increase in the first ionization energy, right? So my question to you is, which of these three you would expect to have the lowest value for the first ionization energy? I'm sorry? Magnesium would be the first one, followed by silicon, and then sulfur. Exactly. So that's the answer for A. Magnesium, then silicon, then sulfur. All right, very good. The next series is arsenic, nitrogen, and phosphorus. So based on what I see here in the periodic table, they're in the same group, right? Arsenic, nitrogen, and phosphorus are in the same group. And remember we said, going down any group, what you'll find is that the first ionization energy will decrease, all right? So which of these would you place first as having the lowest first ionization energy? Between arsenic, nitrogen, and phosphorus, which would have the lowest first ionization energy? And you guys out there in Zoom, please feel free to chip in with your responses.
Arsenic.
I'm sorry?
Arsenic.
Arsenic would be the first one, yes. Followed by
Phosphide.
phosphorus, and then
Nitrogen.
exactly, so that's it. So that's the answer for B, all right? Now, what about C? C says arsenic, germanium, and phosphorus. So based on the periodic table I have here in this classroom, okay, so I see germanium to the left of arsenic, and I see phosphorus above arsenic, all right? So which of these would you expect to have the lowest first ionization energy between germanium, arsenic, and phosphorus?
Germanium.
Germanium would be of the lowest, followed by
Arsenic.
arsenic, and
And then
then
phosphide.
exactly. Okay, very good. All right. Okay, any questions about this? Any questions about this question, this example? Okay, so the other property we're going to look at in terms of how it changes as you go from left to right of a period and down a group is what is called electron affinity. So just as how we have to define the ionization energy, we have to define electron affinity, which is given right here. It is the energy change that occurs when you have an electron added to a gaseous atom, right? So this is kind of like the opposite of ionization energy, because remember we said that the ionization energy of an element is the amount of energy needed to remove an electron from a gaseous atom. Electron affinity is the amount of energy, change when an electron is added to a gaseous atom, right? And what you're going to find is that that energy change, which is called the electron affinity, is going to be negative, all right? In other words, it's exothermic. So what you'll find is, and this is a general trend, is that as you go from left to right of any period, the electron affinity will become more and more negative, and as you go down a group, the electron affinity will become less negative, all right? And what you'll find as a result is that nonmetals tend to have a greater affinity of electrons, and therefore the electron affinity will be more negative for nonmetals compared to metals. Okay, so this is, and I'm not going to spend too much time on this because actually understanding all the trends and especially exceptions are a bit more complicated beyond the scope of this course. But basically, we have some numbers here. Another thing that complicates things when it comes to electron affinity is that they're very difficult to determine. So we don't have all the numbers that we would like for electron affinity. But the general trend is observed. Basically, as you go from left to right, electron affinity becomes more negative, and you can see that to a certain extent for period 2, where you start off with lithium, which is minus 60. Here it says electron affinity of beryllium is greater than 0. They can't tell you what the exact value is and so on, but basically there's a general trend. It falls, the trend is kind of halted here, so to speak, and then it kind of goes up and down, but the general trend is that it becomes more and more negative as you go from left to right of any period, all right? And that's all we're going to say about that, because this is a bit more complicated compared to first ionization elements. Okay, metals. These, of course, are elements where, if you look at the atomic structure, they have a relatively small number of electrons on their outer shell. And this is particularly true for the representative elements. And basically, they form ions by losing those electrons to form the ions with the plus charge, the cations. And we see that, for example, in the case of aluminum, where the atom will lose 3 electrons to form the aluminum 3 plus ions. And this is basically displayed by metals in the S block regions, the D block region, and F block regions, and some P block elements like lead and tin. So those elements basically are metals, and they display the ability of easily losing their electrons on their outer shells. And this leads us to what is called the metallic character, right? So basically, this is another trend that we're going to look at when it comes to periodic trends in the periodic table. So basically, the summary of this is what you see here, right? The metallic character increases as you go down the group and increases as you go from right to left of any period, right? So that's basically it as far as metallic character is concerned, which is related to ionization energy and atomic radius. Basically, the greater the atomic radius, the lower would be the ionization energy, and therefore the greater would be the metallic character, and the converse would be true. All right, so that's metallic character. And then we have non-metallic character. Of course, non-metals basically have a larger number of electrons in their valence shell. They tend to gain electrons to form anions, and therefore, and also all non-metals are P block elements with the exception of hydrogen and helium. And the trend in terms of non-metallic character is basically the opposite or the reverse of what we just described with respect to metallic character, which means that non-metallic character increases from left to right of any period and from bottom to top of any group. Okay, and then we have a minority group of elements which are not metals or non-metals. They're called metalloids, and that's because they have some characteristics in common with metals, other characteristics in common with non-metals, and there are only 7 of them. They're listed here. Let me go back to the previous slide. I skipped over something. In the periodic table, I don't see that in this periodic table that we have in the class here, but for most periodic tables, you see a thick line, a stepwise line, which basically represents the line of demarcation between the metals on the left and the non-metals on the right. And you have some elements immediately on one side or the other. Those are called the metalloids. And there are 7 of them, which is listed here. All right. These are elements which display both metallic and non-metallic properties. All right. So here is a summary of the different trends that we just discussed. So just to briefly recap, right? In terms of, let's say, atomic size, remember we said that the atomic size decreases as you go from left to right of any period, or increases as you go from right to left, and increases also as you go from top to bottom of any group. In terms of the first ionization energy, that increases as you go from left to right of any period, and decreases as you go from top to bottom of any group. In terms of metallic character, basically that follows the atomic sizes, right? So again, it goes as you go down any group, the metallic character increases. As you go from left to right of any period, the metallic character decreases, and then non-metallic character would be simply the opposite of metallic character, all right? So that's basically what we have covered so far in this chapter. So based on what we have covered, let's see if we can answer the following examples. The first of which says, in each set, indicate which is the more metallic element. So remember, metallic character increases going from right to left and increases going down any group. So in this case, we have barium and calcium. So which of these two, based on their relative positions in the periodic table, which of these two would you expect to be the more metallic element? Which of these two would you expect to be the more metallic element between barium and calcium? Where are barium and calcium located? You're located in group 2A in the periodic table, right? So which one of those two would be the more metallic element? Well, remember, as you go down the group, the metallic character increases, right? So which one of these two would have the more metallic character? And you guys out there in Zoom, please feel free to chip in.
Barium.
Exactly, barium would be the more metallic element. Okay, in the case of B, antimony and tin, which would you expect to be the more metallic between those two? Excuse me.
Tin.
Exactly. What about C, germanium and sulfur? Okay, so germanium is there, and sulfur is in the period above to the right. Okay, so which of these two you expect to be more metallic?
Germanium.
Okay, very good. All right. So that's that. Let's see what's next. Okay, just some comments here about the noble gases. Those are the elements that are in group 8A or group 18, depending on the numbering system used in the periodic table. And the thing about these elements is that they are very inert. That's why they're called noble elements or inert elements. And the reason why they're inert is because they have a full complement of electrons in their outer shell, and therefore they have no great need to combine with anything else to complete your octet, because your octet is already complete. Now, there are a few instances where scientists have been successful in combining a couple of these elements with other elements to form compounds, but they have to employ some real stringent conditions in order to achieve that. And also, some conditions would have to be created in order to maintain the compounds that are formed. That is certainly true for compounds that have been made from argon and krypton and xenon. I'm not sure about radon, right? But so far, last time I've checked, nobody has successfully made compounds by combining elements with helium or neon, right? So as far as I know, nobody has been able to successfully cause these elements, helium and neon, to react with anything to form compounds, right? But people have successfully made compounds with argon and krypton and so on. But as I said before, special conditions are required for that. And if you just leave those compounds out in the atmosphere, in the regular atmosphere, they will just decompose, all right? Because they're very unstable. Okay, and then let me just say something about flame colors. Now, remember we talked about the fact that you can have electrons being promoted from lower energy shells to higher energy shells. Energy will be required to do that, and then immediately after, those electrons will fall from the higher shells to the lower shells and emit radiation. And this can be used to help in terms of identifying certain ions using the flame test. Basically, what you do in the flame test is that you dip a piece of nichrome wire, which is an alloy of nickel and chromium, which is not reactive or is very inert, it won't react with the ions themselves. You dip it into the ion solution, and then you put that into a flame, and the result will be, depending on the composition of the ion solution, flames of different colors. And the colors arises from the fact that when the electrons are promoted from a lower shell to a higher shell, and then they fall back down, they emit radiation of a particular color depending on the element. So these are just some examples of the different types of colors. For example, in the case of sodium, you see a yellow flame. If you are cooking at home and let's say you have, I don't know, you're cooking something which contains salt and you have some spillover onto your burner, you might see a yellow flame that is due to the sodium in the sodium chloride, for example. And these are some other colors as well. Calcium has an orange-red color and so on. Potassium is kind of blue, etc. All right. So we can use these to detect the presence of certain ions in an aqueous solution. Okay, some other things I want to talk about with respect to group 7A. Now, group 7A, these are known as halogens. And what they all have in common is that they are very good oxidizing agents. Now, the strength of their oxidizing power is related, when you compare them to each other, is related to their positions in that group. Whereas fluorine will have the highest oxidizing power, and then that oxidizing power decreases as it goes from fluorine to chlorine down the group. All right. So we can see that comparison in this example here. Now, this example, what this person is doing is bubbling some chlorine into a solution which contains the iodide ion. Now, chlorine has a stronger affinity for electrons compared to the iodide ion. So what's going to happen is this. The chlorine will react with the iodide to form the chloride ion, and iodine will be formed. All right. So basically, the chlorine atoms will gain the electrons from the iodide and become the chloride ion, and the iodine molecule will be formed. And that is what is being shown here. Both the chlorine and the iodide would be relatively colorless. Chlorine is actually a kind of pale green color, so the solution is colorless. And then when the iodine is formed from the iodide, when it dissolves in carbon tetrachloride, which is added to this, the iodine will dissolve in the carbon tetrachloride to give this purple color or violet color being formed. All right. So that basically shows you the relative oxidizing power of chloride to iodine to the iodide, or I should say chlorine to iodine. All right. So basically, what we can say is that the greater the oxidizing power, the more likely that particular halogen will displace the other halogen from its solution. So chlorine will displace iodide, bromide from their solutions, but fluoride will displace chloride, bromide, and iodide from their solutions. All right. Okay, and that's all we're going to say about that. As far as reducing agents are concerned, the elements in the S block, which would be the groups 1A and 2A elements, will displace or will donate electrons to something which is oxidized. So as a result, if you look at the reactions of the group 1A and 2A metals with water, what you'll find is that they will displace hydrogen from water according to this equation. I'm going to use potassium as an example. So potassium plus H2O will give potassium hydroxide plus H2O. All right. And to balance this, you're going to need a 2 here, 2 here, and a 2 here, right? So basically what will happen is that the potassium will displace the hydrogen from, or some of the hydrogens from water to form potassium hydroxide, and the displaced hydrogen will be formed there, right? And you're going to see that this reactivity actually increases down the group. So lithium will do the same reaction, but not as vigorously. Then you have sodium, then you have potassium. So as you go down the group, the reaction becomes more vigorous between those elements and water, all right? And the reason why that happens, as stated here, is that those elements on that side of the periodic table, they have low first ionization energies with it, which increases as they go down the group. So therefore, as they go down the group, they're more likely to reduce water, and therefore the reaction becomes more vigorous. All right. Okay. And then I think this is the final thing in this chapter. It says that acidic oxide produces, this is talking about the different types of oxides. You have acidic oxides, you have basic oxides, and then you have amphoteric oxides. So the acidic oxides are those oxides which, when added to water, produces an acidic solution. A basic oxide producing a basic solution when added to water, right? Now, generally, what you'll find is that acidic oxides will be oxides of nonmetals, while basic oxides will be oxides of metals, right? And then we have amphoteric oxides, which can behave as either an acid or a base, depending on what it reacts with. So it can, if it reacts with an acid, then it's acting as a base, but if it reacts with a base, then it's acting as an acid. Basically, that's what it comes out with, right? And what you're going to find is that these elements here in these, I don't know what color this is, something looking like yellow. They tend to form amphoteric oxides, right? The metals to the left, they tend to form basic oxides. Those to the right, they tend to form acidic oxides, but these here tend to form amphoteric oxides. Okay, so that's basically it as far as this chapter is concerned. So what I'm going to do now is go to the assignment. Okay. Oh, okay. So let me go here, because now I think we can do the rest of the questions in the assignment. So okay, so I think the last question we looked at was question number, or part, we did part C, right? So part D is where we're gonna continue from. Okay, so the first question in part D is asking define ionization energy. We just covered that earlier, right? So what do you understand by that term? Anybody?
Yeah. Saying energy required to electron from the state gaseous atom basically given on that
Required to remove
an electron from a ground state
an electron from a ground state. And this is very important, gaseous atom. All right. Okay, so that's the definition of ionization energy. Okay, so the next question is, what trend in ionization energy do you see as you go down a group on the periodic table? So what's the trend? Is it increasing or decreasing?
Decrease.
I'm sorry, repeat that?
Decrease.
Decrease, exactly. Okay, so the next question is, what causes this trend? Why is it that as you go down the group, there is a decrease in the first ionization energy?
Well, one of the reasons is that as you go from top to bottom, there's more electrons, so the first
Is that?
there's more overall electrons than more shells, so as you so the valence electrons are getting further from yes, so
Okay, so what Mr. Simon, you were saying that as we go down the group, the inner core electrons repel the valence electrons pushing them further from the nucleus making them easier to remove, making them easier to remove. And that's it. Alright? Okay. So that's the answer for number 3. Number 4, what trend in ionization energy do you see as you go across a period? Assuming left to right, going across a period left to right, what do we observe in terms of the first ionization energy? Does it increase or decrease?
Increase.
Increase, okay, very good. So the next question is, what causes this trend? All right, I'm gonna clear this because I'm gonna need a space. What causes this trend? Why is it that there's an increase in the first ionization energy as you go from left to right of any period? So this is increase, right? So why is it that we observe this trend? What happens as we go from left to right? Let me start you off. As we go from left to right of a period, what happens? As we go from left to right of any period, what changes are taking place in the atoms? There are 2 changes. As we go from left to right of a period, what happens? Anybody? As you go from left to right of a period, let's say we take period 2, starting with lithium. What are the changes that are taking place in the atom? Going from lithium to beryllium, and then boron, then carbon, nitrogen, oxygen, fluorine, and then neon. Well, anybody out there in Zoom can answer that question?
They gain additional protons.
Okay, so protons are added to the nucleus. Oops. And what other changes are taking place? Or what other change? So one change is, as you correctly said, protons are added to the nucleus. And what? I'm sorry?
Is it politically because more overall electrons are being added to the specific.
Okay, so more electrons, or let me say, electrons are added to what? I'm looking for the magic word here. Are added to, or magic words. Are added to what? We're adding electrons to what exactly? You're adding protons to the nucleus, that is true, and you're adding electrons to what? You're adding electrons to the same what? What's the next word I'm looking for here? You're adding electrons to the same,
Valence shell.
exactly, the same valence shell. All right? So basically, since you're adding electrons to the same shell, that means that the screening effect will be the same for those electrons in that shell. So basically, as a result, the valence electrons will be pulled closer to the nucleus and become more difficult to remove, become more difficult to remove. And that's the reason why we see that general trend of increasing ionization energy, or I should say increasing first ionization energy as you go from left to right of any period. All right, okay, so, excuse me. Number 6 says circle the atom in each pair that has the greater first ionization energy. All right, so let's start off with A, lithium and beryllium, right? Which of those two would you expect to have a higher or greater first ionization energy? I'm sorry? Beryllium would be correct. What about B, between sodium and potassium? Which of those two would have the higher first ionization energy?
Sodium.
Sodium would be correct. Chlorine and silicon. Which would you expect to have the first, the greater first ionization energy?
Chlorine.
Chlorine, correct. What about D? Between calcium and barium, which would have the first the greater first ionization energy?
Calcium.
Calcium. Okay, phosphorus and argon, which would be higher in terms of first?
Argon.
I'm sorry?
Argon.
Argon. And then lithium and potassium.
Lithium.
Okay, very good. All right. Let me clear this. And scroll down to number 7. I think that's the last question. Yes, that's the last question. All right. So in this case, you're going to rank the given series in each case according to the first ionization energy from the lowest to the highest, right? So let's look at these first 3. Which should you expect to be the lowest of these 3 in terms of the first ionization energy? Magnesium, followed by silicon, and then sulfur. All right. What about B? Which would be the lowest of these 3?
Barium.
Barium, followed by
Calcium.
calcium, followed by.
Magnesium.
Okay, what about C? Which would be the lowest?
Bromine.
Bromine, followed by
Chlorine.
chlorine, and then chlorine. Okay, what about D? Now, D, they have barium, which is there, copper, which is up further, and then neon, which is up further to the right. Okay, so which of these would have the lowest first ionization in? Barium, okay, followed by copper, and then neon. Okay, very good.
Even with the different places. It's
Yeah, exactly. Basically, as you go from the bottom left corner to the upper right corner, the first ionization energy will increase.
It almost makes them.
Exactly. And then the last one, silicon, phosphorus, and helium. So which would have the lowest? Okay, so silicon is there, phosphorus is there, and helium is okay. So which would have the lowest of these three?
Silicon,
Silicon, followed by,
phosphorus.
and then, of course, helium. All right, very good. Okay, so that's basically all that is done. So we have completed this assignment. So what I'm gonna do now is set up a Dropbox for this one. Okay, so let's see, assignment. Number 8. And let's see. Uh, okay, I'm going to um I'm going to put the deadline as the 15th. So let me do this. Okay, so it's going to be due on the 15th at midnight, right? So make sure you have it submitted by then. Before I forget, I need to post an announcement about this. So your next test, I'm going to schedule it for. I have the date written here somewhere. Okay, I'm going to schedule it for the 25th. All right. Yeah, I'm going to schedule it for the 25th. Let me make sure I write that down. And that would be based on everything that we have covered up to today. All right. So I'm going to grade your assignment ASAP and get it back to you so that you can have that to help you to review for that test. All right. Oh, before you leave, there's something I found interesting online. As it relates to what we're just discussing. If I can find it here. Okay, so here's something I found on Facebook. Based on what we just discussed today, right? This basically is supposed to summarize what we just learned, right? The trends, atomic radius, ionization energy, and so on. But one of them is incorrect. Can you tell me which one is incorrect? One of them is incorrect. We learned about atomic sizes, we learned about ionic radii, we learned about ionization energy, electronegativity. Well, we didn't talk about electronegativity, but that's correct for electronegativity. But one of them is,
Would be metallic there.
I'm sorry?
Would it be metallic there?
Exactly, the metallic character one is incorrect,
So I
right?
know we did the barium and calcium, and we said that barium was.
Exactly, right. So this basically underscores the importance of being careful when you look at online sources because you can get wrong information. I mean, I can tell you stories about wrong information I've seen online. And this is one example of that, all right? Okay, that's it for today, folks. I'll be in my office today from 2 to 5. If you have any questions. Take care. Okay, and